Now, again, as with all graphical techniques, we're still just eyeballing. And that's not good enough. It's a good way to start. It's always a good way to get a feel. But we'd really like to put a probability on whether or not our population is normal. And to do a probability, you need an inferential stat. And as I mentioned, there are several of these, but a good one is the Shapiro Will test for normality. And that's the one that's easy to do in R. It's widely used, and that's the one we're going to use in here. And it's very simple to do in R. You just use the command shapiro.test, and of course there's the variable that you're testing. And here are the results. It's just that simple. You'll see that it gives you a value for W. W is the value of our inferential stat. So the Shapiro-Will inferential stat is identified by W. And it's just like when we do a t-test, the inferential stat is t. Or a chi-squared, it's chi-squared. So that's all that is, right? That doesn't tell you much. The main reason for doing an inferential stat is to get a p-value. You see that our p-value in this example is much less than 0.05. Just to make clear what we're looking at, you see that this is 1.867 e to the negative 6. That's exponential notation. It's 1.867 times 10 to the negative 6. So you need to put 5 zeros in front of this value to get your p-value. So make sure that you're reading these correctly. So of course that's much, much less than our alpha of 0.05. And so what is our decision? If p is less than alpha, then we reject the null. And remember again what a p-value is. So I ask you to memorize this definition. If the null is true, what is the probability that I would get the results I actually did obtain, or results even more extreme? Okay? And so that's what this p-value tells us. So we have a p-value, and it's very, very low. It's extremely, extremely low, far, far less than 1%. So it's saying, if the null is true, what's the probability that I would get the results I actually did obtain, or results even more extreme? Well, that probability is 50, it's 50, decimal point 5 zeros and a 1. It's far, far below, less than 1%. So the probability that I would get these results if the null is true is very low. That suggests that the null is false, and that's why we reject the null. Okay? Think about the definition of a p-value. Okay, so we're going to reject the null, but what is it? I haven't told you what the null is. And for this test, the null is that the sample comes from a normal population. Okay? Now, you didn't know the null, and that's fine because you're just learning this test for the first time. Normally, you will be setting up the null in your experiment. This test, the null is already set up for you. And so the null is that the population, that the sample comes from a normal population. Remember that these stats are done on samples, which we infer to populations. So again, remember that we assume that the null is true. So we always are going to start out by assuming that we are working with a normal population. All right? Of course, the alternate then is that the sample comes from a non-normal population, mutually exclusive. So we rejected the null, reject, and so we can say that the data support the alternate. The sample comes from a non-normal population, which is what we suspected from the frequency histogram, which is what we suspected from the QQ plot, but now instead of just eyeballing it, we actually can put a probability on that. And so that's what this says right here. We reject the null. The sample does not come from a normal population. And what's our level of uncertainty? Well, it's much, much less than 1% chance that that null is true based upon our data. All right. So when are we going to use this? Well, we're going to use it a lot. Whenever we can, we're going to check normality. It's a very, it's assumed in a lot of the tests we do. So we always want to go ahead and check that because, if we reject the null, if we find that it's actually not from a normal population, that's usually not a killer, but it's good to know. Understand that the Shapiro-Will test is very powerful, which means even if the population is very slightly non-normal, just a little bit skewed or has a little bit of kurtosis, Shapiro-Will will reject the null. So if it's not, it almost has to be perfectly normal for Shapiro-Will to not reject the null. Well, that can be a disadvantage. If you run something and it always rejects the null, that may be a little bit too powerful. That may not be very informative. But again, it's a very solid test, and so we're going to continue to use it. Although it's very powerful, it still is a very reliable test. You'll also remember from last week that I did suggest that because of the central limit theorem, the normality of the actual population is perhaps not necessary or not a huge deal. You'll remember that we are taking samples from the population. And if we take a huge number of samples and we look at their distribution, that's going to be a normal distribution. So any sample you take will belong to that normal distribution, and it will also belong to the population of interest. So you can be confident that your sample actually does come from a normal population based upon the central limit theorem. And so if Shapiro-Will rejects the null and tells us that we don't have normality, again, it's not a deal breaker, but it is nice to know, and it is going to influence our decision-making process. Perhaps we will just look at our stats a little bit more closely. Perhaps we will switch to a different stat. Perhaps we'll do like a non-parametric stat. And so that's why we're always going to test for normality. We're usually okay, even if we are not working with a non-normal population, unless we have severe deviations from normality. Most of the parametric inferential stats that we'll work with in this class are very robust, which means that they're okay if you don't have a normal population. However, if you have severe deviations from normality, that's when you perhaps need to try different tests like a non-parametric test. Let me give you an example. This is the catch data from one of our lake sturgeon studies. So it's CPUE is catch per unit of effort, and this is for lake sturgeon, which are a type of fish. So here is all the different CPUEs we got in our sampling. So 1 fish per hour, 2 fish per hour, 3 fish per hour, and you can see how many of our samples caught that many lake sturgeon. And what you probably notice is this bar right here, which clearly is the mode, and that's 0 fish per hour. And so what does that mean? That means most of the time when we fished, when we threw out a net, we didn't catch any lake sturgeon. It's not because we're bad at catching lake sturgeon. It's because they're rare. They're a state endangered fish. And so most of the time we got 0 fish per hour, and then we did catch some fish. And this is a typical distribution. A lot of times you're going to have something, especially if you got you're recording counts of something, you're going to get a lot of zeros. And so, excuse me, this is what I would consider a severe deviation from normality, and I would have a difficult time justifying running a parametric stat on data with this distribution. We run those data through the normal QQ plot. You see here's our QQ line down here, and you see tremendous deviation from that line. You see down here, it's not so bad, but up here, clearly that suggests non-normality. And if we run the Shapiro test on it, you'll see p-value is 2.2 times 10 to the negative 16. So put 15 zeros in front of this 2, and then a decimal point, and that's your p-value. And again, what is a p-value? What is the probability, if the null were true, that I would get the results I got or those more extreme? And that probability in this example is 15 zeros and a 2. I mean, it's almost non-existent. And so that suggests that the null is not true. We reject the null, which is that the data are normal, and we support the alternate. Okay, so the take-home message is this. Test normality when you can. It's always good to know if you're working with normal data. Slight deviations from normality to moderate deviations from normality are usually okay. Most of the tests are going to be robust, and also the central limit theorem suggests that we'll be fine. What is a severe deviation from normality? Sometimes that's a judgment call. Okay, so you have to do the best you can, and that's where experience comes in. And we'll get a lot of experience in this class, and I'll give you my opinion on what is severe, and you will formulate your own opinion. And that's it. I do not want to keep my ink annotations. So appreciate you listening. If you've got any questions, please let me know, and have a good evening. Later.